if every person, man, woman, child in the United States went ahead and put in $57,000, okay?
That's a brand new truck.
Yeah, I mean, that's a truck, basically, or a vehicle, right?
332 million.
Every person here needs to put $57,000 into it, and we can get us back to zero. It's crazy, right? That's a crazy number. And it continues to grow. You can go online, you can just Google federal deficit tracker, and it'll just have the number. It just keeps growing and growing and growing.
We're at 332 million.
Yeah. What? You're at what?
People. Yeah.
Yeah, okay, 332. Okay, so maybe it's not 57,000. Maybe it's 50.
It's like
Yeah, it's bigger now, right? Because so, yeah, it's depressing, but let's continue. So what do we do, the United States? What do we just keep printing money, right? We print money. Print it. All right. All right, so exponential functions. I'm ready to define what an exponential function is explicitly. I've given you some examples, right? An exponential function is any function of this form. F of x equals a raised to the x. Now the a here, we call the a the base of the exponential function. And so the way that you would say this is the base A exponential function. Or you could say that's an exponential function of base A. However you say it, you need to include what the base is when you say it verbally. Now there are some restrictions on this A. There are some restrictions. A can't be any number you want. Here are the restrictions on A. First of all, A has to be positive. If A is negative, then that's a whole different type of function that we don't get into at all in this class. They're not even called exponential functions anymore. So the A here, the base, must be a positive number. And the other condition we have on A is that it can never be 1. And the reason it can't be 1 is because what is 1 raised to any power? 1. So that particular function wouldn't do anything. It would be boring. It would just be 1. It would be like a constant, just a flat line. So in order to remove that, we just go ahead and say, don't ever let A be 1. But A can be anything else. So what were the examples I gave you for the bases? First example with the rectangles was 2, right? The second one where I was tearing was 1/2. And then the bacteria was 3, right? Those are all examples. Now, when you go and you graph these, all right, so what do these look like? What do they look like? Well, we have two scenarios. And it's kind of like with parabolas. Remember with parabolas, parabola either opens up or down. Those are the only ones we studied in here, up or down, right? With exponential function, it's either going to be this one or that one. There's only one of two different scenarios. Here's the first one. First, this point must be on the exponential function. The point 0, 1 must be there. And that actually is for both of these. Now, can you resolve in your mind why that's true? No matter what exponential function I ever give you, who cares what the base is? What's any number raised to the 0? 1. So no matter what, that point should be included, shouldn't it? 0 goes in, 1 comes out. All right, now, if the A that you're looking at for your base, if the A is bigger than 1, so remember, it can't be 1, right? But if it's bigger than 1, then what you're going to have is a graph that does this. As you move to the right, the graph is going to grow, almost like a parabola does, okay? Almost in terms of the shape, it's curved. But if you go to the left, the graph is going to die down towards the x-axis, and you will have a horizontal asymptote there. And this is what we call exponential growth. We call it growth because as you move from left to right, like you would read a book, it grows. Now, if the A you have is smaller than 1, but remember, it must be positive, right? So greater than 0, A has to be greater than 0. So if the base you have is between 0 and 1, then what you're going to get is that picture flipped over, the y-axis. So you're going to have to the left, it's going to grow, and then to the right, it's going to die down towards the x-axis, and you'll have a horizontal asymptote there. And this is called, anyone know what this is called? Exponential decay. Decay. So exponential growth is when your base is bigger than 1, and exponential decay is when your base is less than 1 but bigger than 0.
If it's still left, we're going to have negative x value.
Yes, you would have negative x values over here. So I'd like to show you with the example we did earlier. Let me show you this scenario. So the example we looked at with the rectangles, right? What was the function we came up with when we were folding? 2 to the x, right? 2 raised to the x. So this is the base 2 exponential function. And so if I were to want to graph this, I know it's going to look like this, right? In some respect, it's going to look like this. To the right, it's going to go up, and to the left, it's going to die down and get closer to the x-axis. Let's see why. So let me plug in some values. Now, keep in mind, I'm looking at this function right now, and I'm not thinking about rectangles and folding paper anymore. I'm just going to start plugging some values in. So I'm going to start a little bit lower. I already plugged 0 in earlier. I got 1. I plugged in 1, I got 2. I plugged in 2, I got 4. I plugged in 3, I got 8. I plugged in 4, I got 16. Right? We did that already. What we didn't do is plug in negative numbers. So let's try some negative numbers. How about negative 1? Well, that's 2 to the negative 1, isn't it? And remember, a negative exponent really means 1 over 2 to the positive exponent. And that's really 1/2, isn't it? So that means if I were to graph it, let me do a separate graph over here. If I were to graph it, when I plugged in 0, I got 1. When I plugged in 1, I got 2. When I plugged in 2, I got 4. When I plugged in 3, I got 8. Right? Something like that. I'm going kind of quick there, but you get the idea? Now, when I plug in negative 1, I only go up 1/2, right? And then what happens if I plug in negative 2? You get 2 to the negative 2, and then that's 1 over 2 squared, but then that's 1/4. So we get 1/4, which is even smaller than 1/2, right?
So you're never going to get to 0.
You never get to 0. That's right, you never get to 0. An exponential graph of the form a to the x can never be negative. Now, we can always shift it up and reflect. Remember all the transformations? So you could possibly have an exponential function go negative, but not the basic one. The basic exponential function, a to the x, that right there will never be negative, ever. Got it? This will always be greater than 0. Never will that ever be 0 or negative, unless we move it, right? Okay, so, and I could keep going, right? Keep going. Do any of y'all ever buy like your deli meats or anything from H-E-B, like at the deli? Go ask for 2 to the negative 2 pounds of turkey. See what happens. And then watch carefully that they don't spit in your food, right? 2 to the negative 2, quarter pound turkey, right? That's what that means, right?
Have you ever done
I've done it.
that? Really?
Yeah, I had to.
What was the reaction?
Blank stare. A blank stare. Excuse me? Never mind. Quarter pound, please. I had an experience at H-E-B about 1.5 years ago where I needed to get a balloon. And I just went and grabbed one real quick. 2 balloons, actually. I grabbed 2 balloons and went to the register. And it said, when I grabbed them, it said they were, what did it say? $1.50 each. They were $1.50 each. They were just little cheap little boons. I took it to the register. They didn't have a price tag on them, right? So I told the girl behind the register, I said, hey, these are $1.50. So she breaks out her phone. And I'm like, okay, she's going to look up the SKU and, type it in, type the number in. Nope. She needed to add $1.50 to $1.50. And I just about lost my shit. I was like, wow, okay, right? So I think, I think one of the problems with our education, I'm on camera right now, be careful. One of the problems with our education is not that the kids coming through, right? It's not that they lack the ability to learn this stuff, but they become so dependent on the calculators that they're never taught to think quickly, so they just go to it, even though if they just stopped for 10 seconds, they would be able to figure it out. So it's become like this crutch, right, which stops people from thinking. Yeah. I heard about a school district the other day, yesterday, I heard about a school district, I forget what state it's in, they are now banning cell phones in middle school. What do y'all think?
It's already banned.
Well, what do like my sister,
here? She was in middle school last year, she can't bring a phone.
You can't take a phone to school?
No.
Really?
But they're banned, yeah.
Is it public school?
Yeah.
Really? That's great. I'm glad to hear
The
that.
whole district, I guess.
The whole district did it?
There's a school in Austin now that has no teachers and it's all run off AI.
Oh, that's crazy.
Yeah.
Yeah,
So,
that's pretty crazy.
Really, they have in history, they have presidents teaching about themselves.
Huh? I don't know. We'll see where that goes, but that could be interesting. That could be interesting.
Dividing by zero is undefined when you break the AI.
Yeah, right. All right, so yeah, don't do that. Don't go to the deli and do that. All right, so you see how we do this table to graph these? Yeah? So in terms of graphing these types of functions, there's not like this big set of steps that we do. You know how we did it for like rationals, vertical asymptotes, horizontal asymptotes, test points, all that stuff? These are kind of easy to graph. The easiest way to do is just make a little t-table, get your calculator out, plot the points, and you're done. Because you know it's got to look like either this or this. All right? Let's look at the 3 to the x next to this one. And I'm going to do it on the same graph. If we do 3 to the x, okay, that would look like, let's see, we plugged in 0, we got 1. We know that's going to happen every time. We plug in 1, we get what? 3. We plug in 2, we get 9. And then 3, we get 27. Notice I'm not using the one with the bacteria, because remember we put x over 12? That was for that particular problem with the hours and stuff. But just in general, it's like a 3 to the x. And then 4 is 81, right? Let's plug in some negative numbers. -1. 3 to the -1? 1/3. It would be +1/3. +1/3. I don't know who said that. Right? That's 1 over 3, which is 1/3. -2 in here. 3 to the -2. 1/9, right? And so on and so forth. So let me graph that one. I'll do this one in red. I'm going to do it on the same axis. They both have that point, right? What's the value of that function at 1, though? 3. So we're up here. And at 2, we're at 9, which is already up here, isn't it? And then at 3, we're off the charts, right? So this grows extremely fast, doesn't it? That grows really fast. And not only does it grow fast, it dies down fast, too. Because when we plug in -1, we're at 1/3, not at 1/2. When we're at -2, we're at 1/9. So it actually gets closer to the x-axis faster. That's what the graph of that one looks like. Do y'all see the difference between these two?
Yeah.
So I hear it a lot, and I'm sure you do too. I hear it because I do this for a living, but I pay attention to it. I hear it in the news, right? They'll be like, violence in San Antonio is growing exponentially, right? They love throwing that word exponential around. It kind of gets abused, right? Because if violence was growing exponentially, then if there were 2 crimes today, then in 10 days there would be 1 million crimes. You know what I mean? Like it's not truly exponential, right? They just say that to make people have the reaction of it's growing fast, right? And you can see here that the number, the base, dictates the speed at which it grows, right? The bigger the A, the faster it grows. The smaller the A, well, you have to be careful when you say that. The smaller the A. If A is bigger than 1, as long as this number is bigger than 1, like if I did, let me do it in green. If I did this graph, let's go 1.2 to the x. Is that growth or decay?
Growth.
That's growth, right? How is it related to these two, though? Well, it would have this point, right? But now it would do something like this, and it would be above over here, but it would still die down. So the green, the 1.2, doesn't grow as fast as the 2 to the x. The 2 to the x grows faster than this, but the 3 to the x grows faster than that, right? So the smaller the A is, the less the growth is, so long as you're bigger than 1. Yeah? Once you get less than 1, the graph flips over, and now you have this. Okay? So, all right, are we good? Are we good? Let's try some transformations of these, all right? I'm going to give you an exponential function. Oh, wait, hold on, time out. Domain and range, I forgot to say it. Look at both of these graphs. What can you tell me about the domain? All real numbers. Domain, negative infinity to infinity. Range, 0 to infinity, not including 0. So you can graph, the graph goes both directions, right, forever. That's your domain. The range is only from here up, right? From here up, but not including 0. Your graph never actually hits 0. All right, here we go. I'm gonna now ask us to do some transformations. I want us to sketch. And when I say sketch, that means just a real quick sketch. Doesn't have to be super precise. Let's sketch f of x equals negative 2 to the x plus 3. So we've done transformations before in this class. I believe it was on your last test, right? Like the first question or so on your last test was like, I think that was piecewise. But it was like, yeah, take a function and move it, right? Flip it over, that sort of thing. That's what we're doing here.
So for that, A isn't actually equal to negative.
Yeah, so you have to understand what that means. When I write negative 2 to the x, this really means negative 1 times 2, times 2 to the x. Right? That negative is not with the 2 being raised to the x. It really means this. All right, so let's start. Ignore that. We know what that looks like, right? 2 to the x. It looks like this. That's 2 to the x. All right. What does that look like? Reflected, right? Which way? The negative is in front of the whole thing. X-axis. Reflect that over the x-axis. So we have reflect over the x-axis. That's coming from that right there. So let me draw that reflected over the x-axis. So it's going to look like this now. Right? And then we still have that horizontal asymptote here. That all right? Now we have the plus 3. Up 3.
With the inference, it's up.
Pardon me? Yeah. No, it would be up with the x. I'll do an example of that. I'll do one of those.
So you could never. You're supposed to do the reflection first, right?
Yes. Good question. You do the reflection first. Do it like order of operations. And what I mean by that is if I were to ask you to plug a number in here, right, and figure out what this is, this will be the last thing you do. So that's going to be the last transformation you make as well. So let's see. I take that and move the whole graph, what, up 3? How do we do that? Well, this point, can you all tell me exactly what that point is? 0, no, the one that we reflected. It was 0, 1, wasn't it? And now it becomes 0 what? Negative 1. That point gets moved up 3. So where is it now? 1, 2, 3. Right here, right? This is the point 0, 2. What else moved up 3? The horizontal asymptote moved up 3. So we should move it up 1, 2, here's 3, right? Here's 3. Or horizontal asymptote should be out here now. See? So we reflected it, and then we're moving everything up 3, like that. And then we draw our graph through it. Again, it's a sketch. Doesn't have to be perfect. Y'all understand that?
Yep.
What's the domain and range? Domain of this is all real numbers. The range is the part that's going to change now because I've moved it, reflected it. So the range of this green one is everything from here down forever, right? So we would say negative infinity up till 3, not including 3. Negative infinity to 3, not including 3.
It's a very lonely 3.
Yeah, so this is why I was saying in general exponential functions can be negative, but not if it's just a to the x. If it's a to the x, then it's definitely not going to be negative. But if it's something that's been tweaked, then it could be.
When it's negative, it's because you're multiplying something to the base, right? So a negative number to the base.
Yes. Yeah, but I could not do a negative here, and I could just move the graph down, right? If I took this black one and just moved it down, then it would have some negative values.
I'll talk about what you flip it.
I'm not sure I understand the question. You sure? Okay. How about this one? Sketch this one. F of x equals, let's go 2 to the x plus 3 minus 4. Oh, you know what? Yeah. Yeah, we'll keep it. We'll keep it. All right. So this is like 2 to the x, isn't it? It's like 2 to the x. So we know the basic function. What does the plus 3 being added here with the x do? What type of shift is that? Left or right, up or down?
Left.
It's left, right? Remember, left and right shifts happen right near the x, and it's opposite of what you think. So this plus 3 really means to the left 3, right? Left 3. And what does this mean? Down 4. So we're gonna take the 2 to the x. Here's 2 to the x. That's 2 to the x. And I'm going to take that thing and move it left 3 and down 4. So look at what happens to this point. What happens? It moves to the left 3. 1, 2, 3. That's now negative 3 there. Okay? And then down 4. 1, 2, 3, right there. And then down 4. 1, 2, 3, 4, right there. What is that point? Be careful. What is that point? It went
Negative 3,
negative 3, negative 3, because we were up at 1 already, right? So we went from here, we went down 4. You all got that? Now, I'm going to draw the same thing, right? This exponential. Where did the horizontal go? Where does the horizontal asymptote go? It used to be here. It went left 3. That doesn't change it, does it? If it goes left 3, it's still there, but then down 4. So if we go 1, 2, 3, here's negative 4. It's out here. So my graph is going to come down to it like that. Any questions on that?
Will it ever have a vertical asymptote?
exponential functions do not have vertical asymptotes. So what is the domain of this one? What's the range? Domain is everything again, right? And the range in this case, let's see. We're going to go from here up forever, right? So from -4, but I'm never -4, right? Up to infinity. All right or no? What would be different if I had changed this problem from 2 here to 1/2? The starting function would be like this, wouldn't it? That would have been 1/2 to the x. And then that one we move what? Left 3, down 4. And so it would look like this. Sorry, this is your horizontals this way now. That's supposed to be at 4, -4. All right, I think we're okay. All right, may I proceed to the next concept? Everyone okay? All right, when it comes to exponential functions, as you can see, the bases can be bigger than 1 or less than 1, but positive, right? How many different bases are there then? How many different bases are available to us for exponential functions? How many? We can have 2 as a base, 3 as a base, 2.5, 7.2, any number, right? As long as it's bigger than 0, positive, and not 1, right? So there are an infinite number of possible exponential functions out there, aren't there? Infinitely many. But there are 2 in particular that are extremely important to us, all right? There are 2 very special ones. 2 very special exponential functions. Here they are. The first one is called the base 10 exponential function. And that's f of x equals 10 to the x. The second one is called the base e exponential function. And that's f of x equals e to the x. Here, this is called the natural exponential function. They're not the same. I'll explain. The natural exponential function. Right, so I'm telling you that there are 2 special exponential functions. There they are. One of them, the base is 10. The other one, the base is e. We'll talk about what e is in a second. Let me just start with the base 10, and let's discuss what it is, all right? So starting with base 10, is this exponential growth or decay? Growth, right? 10's bigger than 1. So this is growth. If I were to graph this, I would have 0, 1. And then it would grow extremely fast, wouldn't it? 10 to the, right? 10 to the first power is 10. 10 squared, 100. 10 cubed, 1,000, right? This is growing very quickly. That grows faster than 2 to the x. That grows faster than 3 to the x, right? So very quick. So that's the graph. Now, what makes it special, right? What makes it special? That's really the question. Why is the base 10 so important? Well, it comes down to this. I feel like we've been down this road. So if we have, please let me know. Have we talked about what a number really is? Like the number 352? No? Does that don't look familiar? That when you look at these digits, what each digit represents? Does this look familiar or not? No? Okay. All right. I thought we had, but maybe not. Okay. So I'm trying, right now, just keep things in perspective. I'm trying to convince you why the base 10 exponential function is so important to us, right, to us.
Because we think in base 10.
Because our number system is base 10. Now, what do we mean by that? Have you all heard that? Our number system, we use a base 10 number system. What do we mean? What we mean is this. When you write the number 345, when you're learning this in grade school, right, this means that you have 5 ones, right? That means you have 5 ones. And then you add to that what? This means you have what? 4 tens. And then this digit means you add to that what? 3 hundreds, right? Yeah? And let's throw another number on here. What if I put 7 out here? That means I would have what? 7 thousands, right? We agree? Notice that the 1, the 10, the 100, and the 1,000. Notice that all of those are just powers of 10, aren't they? Like I could have rewritten this as 7 times 10 cubed plus 3 times what? 10 squared plus 4 times 10 to the 1 plus 5 times 10 to the 0. Does this still look familiar? Now, next thing. If I were to put another digit out here, right, another digit, I would add out here up front whatever that digit is, right? I don't know what it is yet. Let's just say it's something here, okay? But that would be whatever I have, it would be that times what? 10 to the 4th, right? Which would be 10,000. Y'all with me? Yes, yes. When I put this digit in right now, when I go put that digit in, how many digits do I have to choose from? Fill that number in, that question mark, fill it in. How many options do you have?
10.
You have 10 options. What are they?
0 to 9.
0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the only options you have, right? To put into that space. How many options? 10 options, right? 10 options. So when you're a child and you're learning this, right? You learn that these are the only digits we have in our number system, right? Those are the only digits we have, 0 through 9. And then from those digits, you make up this number, right? Where each place